Hi there, we are about to find the center of mass of a half a hula hoop which has been drawn for us professionally. Let's start by establishing a coordinate system. And let's put the origin of the coordinate system in the middle of the half a hula hoop. And immediately say, hey, I know where the YCM is by symmetry. It's at the origin, it's at 0. What I'm really interested in is finding the center mass along the x-axis. So we will do that. We will start by establishing a coordinate system. Too late, already did that. We will then write this formula for center mass. 1 over m times integral x dm. And we will say, I haven't divided this up into little tiny masses yet, which I must do. Now, it turns out that it is not a good idea to use the calculus Cuisinart to cut this up into masses because, and I'll draw a couple as though I were going to, and then I'm going to make them go away. If I use the calculus Cuisinart and make cuts all perpendicular to the x-axis, it might be obvious to see that when I make these cuts, a little piece, and this isn't terribly clear because I made these different widths, but a little piece from down here and a little piece from down here will not be the same mass as each other because one of them travels almost horizontal distance along this distance dx, and the other one is traveling upward along that distance dx, and I'm actually going to capture more stuff, bigger dm over here than the one over here. This piece over here is going to be smaller. Remember, they're both infinitely small, but one can be twice as big as the other one. And so, and to actually try to relate how much mass each of those pieces to where they are on the x-axis looks to me to be a very scary proposition. So I'm not going to do that. So I'm going to go back. Get rid of those horizontal cuts. And instead I will use, of course, the calculus pizza slicer, meaning I will make radial cuts. Those are way too far apart. That's not a D anything. I will make radial cuts. There, that's D something apart. And I'm going to, I'll throw another one down here. There's a radial cut, and here's another radial cut. And so I'm going to make a zillion of these cuts, these radial cuts around this hula hoop. And I think it might be clear to see that when I do that, each of the resulting pieces, dm, is going to be identical to every other one. So they all have a certain amount of mass dm. Now I have to figure out how much that is, but at least they're all the same as each other. Okay. Well, how much mass do they have? What is dm? Well, let's consider then that this started off as a straight stick and I bent it into an arc. So the mass is distributed along the length of this stick. This half a hula hoop clearly, so I'll write it up here, is thin. So in other words, the mass is only distributed along this arc length. I'm going to be talking about linear mass density, the mass of this hula hoop, whose dimensions I did not earlier define. I think they tell us that it has mass m and radius r. So this distance is r from the origin to the hoop. That would be the radius. Okay, so the mass of this whole thing is distributed along the arc length. The whole thing could be said to have length L, but in terms of r, the linear mass density of this thing is m over, let's see, what is the length of half of a circle? Well, a complete circle has a circumference equal to 2 pi r, but I'm only doing half of a circle, half a hula hoop, so the length is half this whole circumference, and that's just going to be pi times r. So this is pi times r, half the circumference. Okay, so the linear mass density is m over pi times r. That's nice. What do I do with it? Well, I can say that the mass of each of these pieces, dm, is equal to linear mass density, kilograms per meter of length, if you will, times the length of this little blue piece. Okay, the length of that piece in there, what is that? Well, what this little tiny blue piece is in here is a little tiny arc of the circle. And so I'm not going to call it dx, I'm going to call it the length of that little piece is ds, because it's a little tiny arc of the circle. So dm is equal to lambda times ds. Let's see. That is not really getting me towards my goal. My goal, of course, as usual, is to get everything on the right-hand side of this integral sign over here to be constants, a variable, which usually has been x, but it's not going to be this time, and this a space variable, and d that variable. So if the variable is x, variable, I can spell. If the variable is x, I want this to be in terms of constants, x and dx. In this case, we're actually going to use a different variable, and here's why. I can express the length of this arc length. Let's see, what's the formula for arc length? Arc length, or at least the formula that relates theta, arc length, and radius. Is the theta, this is the measure of an angle theta, of course this is in radians, not degrees, is equal to arc length divided by radius, which means that arc length, S, is equal to theta times r, theta in radians times the radius of an arc. Can I apply that here? Of course I can. The radius of this little tiny angle, which I'm just writing over again here, the radius of that thing is big R. The angle in here, which I'm going to try to mark, the angle of this tiny, tiny little piece of pizza pie is an infinitesimally small angle, and so I'm going to call that d theta. It's a tiny, tiny, tiny little angle. So this equation, the arc length equation, for the purposes of this problem becomes ds is equal to, I'm going to switch these around for some reason, r, which is the radius of the whole thing, times d theta. Okay, why does that make me happy? It does make me a bit happy, says the ringing bell. Let me, in my normal organized fashion, rewrite this down here where I have room. I now have dm is lambda times r d theta. Okay. My equation for center mass, which I must write in green because I'm getting tired of all this black stuff, is x cm is 1 over mass integral x dm. I now have dm expressed in terms of lambda constant, r constant, d theta. If I can get x expressed in terms of constants and theta, then theta would be my integration variable instead of x, which is normally the case. And I can do that, because if I go back up here and choose one of these ds arc lengths, and I'm going to choose the top one, what is the position of that arc length? Well, the position of that arc length, in other words, where is it on the x-axis? Well, it's right here on the x-axis. Okay, can I say something about where this x position is? In other words, this distance from the origin, that's what x means, that distance from the origin. Can I express that in terms of, what do I want? I want to express x in terms of constants, over here on the right, in terms of constants and theta. Can I express x in terms of constants and theta? What the heck is theta? Well, theta, as always, is the angle measured counterclockwise from the x-axis. That's theta. Looks like I've got myself a right triangle. I've got x, I've got the vertical part of this triangle, which I don't really care about, that's y, and I've got the hypotenuse, which is r. So, being a right triangle, I can say something about the cosine is the cosine. I can say that x is equal to r times cosine theta. Boom, x is r cos theta. That makes me happy because I can now write my center mass formula, evidently in green. I'm going to work in the left-hand side here. X cm is 1 over mass times integral x, but I can write x as, here on top, r cosine theta. That's what I'm going to sub in for x, r cos theta. And dm, I've got it right above here, I can write as lambda r d theta. Okay. I'm now giddy because I have r constant, cosine theta, theta is a variable, lambda constant, r constant, d theta. I've got constants, one variable theta, and d theta. Okay, let me pull the constants out. XCM is equal to, I've got two r's and a lambda. R squared lambda over m integral cosine theta d theta. And now that I'm ready to integrate, I should recognize what the limits are, or in other words, over what span of thetas am I integrating. And remember, I measure theta I'm up on the diagram, counterclockwise from the x-axis, which means that I'm going to start measuring my thetas from down at the 90 degrees south of the x-axis, if you will. So my lowest value of theta is going to be negative 90 degrees, or negative pi over 2 radians. Negative pi over 2 radians. And my maximum value will be 90 degrees above the axis, or positive pi over 2 radians. So my limits of integration, the range of thetas I'm going to use is negative pi over 2 to pi over 2. Okay, we're ready to rock and roll. I have r squared lambda over m. Integral of cosine theta d theta. Okay, what's the integral of that? Well, I say to myself, I say, what function would I differentiate to get cosine theta? Well, I know that if I differentiate sine, I get cosine. So the integral of cosine theta d theta is sine of theta. And I put the limits in. I go from negative pi over 2 to pi over 2. And the last thing I have to do is plug those bad boys in and see what I get. I get XCM is equal to r squared. I'm going to plug in for lambda. Where the heck is lambda? Up there somewhere. Lambda is m over pi r. Lambda is m over pi r. That's my lambda. Over m times sine of pi over 2 minus sine of negative pi over 2. Whew, let's finish this bad boy up. XCM is equal to, let's see, I've got an r squared over r, kabang, kabang. I've got an m over m, kabang, kabang, which leaves me r over pi. And then let's see, sine of pi over 2, that's 1, minus sine of negative pi over 2, which is negative 1. 1 minus negative 1 is 2. So my final answer is XCM is equal to r over 2. No, bad. Haha, good joke. Is 2 over pi times r. The 2's on top. 2 pi r. That makes me happy. Thank you so much.